Hello and welcome to part 5 of our 6-part start to finish HEC RAS model with a running wish list in the background. In this part, we'll cover plans. That means today we'll get to know our favorite stick figure icon from the HEC RAS buttons. We're only going to be covering the basics in this series, and we'll only be using the regular old unsteady plan icon. But you can see our familiar mascot animated here as part of the runner. Now this one comes from a combination of some really cool AI and Python scripts for HEC RAS that I'll link to below. Some of you may recognize that it's named after the longtime author and 30-year leader of the HEC RAS team, Gary Brunner. Now, since I've got a soccer shirt on today, I'll go ahead and throw a soccer ball out in front of our running man and see how he does with it. Now, one thing you may notice about the running man button that we'll be covering today is that I don't think he's actually going anywhere. Because who runs with their arms out in front of them like that? Maybe it's dark and he's feeling his way up the hill, but not sure why. But if you look at all of the other plan editor buttons in HEC RAS, they've all got their arms out in front of them. So I think that's why a lot of people call him Running Man, because he must be doing the Running Man dance in place. If you look at MC Hammer here, his arms never swing normally. The animated runner does it, I think, a little more realistically. But you can see with his backup dancers, it's the same thing. They've got their arms out in front. So yeah, I think we'll keep calling him Running Man, even though I know the dance was choreographed into music videos by a woman and first performed way back in the 70s by a woman. So I hate to even call him the Running Man, but that's the name of the dance, and I'll put a link to some fun trivia history on that down below. So today we'll be focusing on this one run button, but there are actually 5 run buttons in HEC RAS that we'll be mentioning briefly. 4 of these feature the Running Man, but this last one, and this is Chris Goodell's claim to fame, does not. So maybe we should have included Running Man coming down the hill here. But keep in mind, before Chris came along, version 2 actually had icons for everything except this one here, which just had these 2 boring letters for the hydraulic design tools. So at least we've got a picture of what I think are grains of sand. Actually, these are grains of sand here, so those are smaller. Maybe these are riprap here. Check this guy out. I think these are drips of sweat coming off this guy running in the sun, because that's the water temperature. So he's running on a thermometer here. I'm gonna have to ask Chris what these plus signs are here. Maybe that's the suspended load to contrast with the bed load. Not sure, but I'll probably just ask you instead of guessing at it here. So today we're going to be focusing on the plan. If we go back to the previous parts, we have set up a project file in part 1, pulled terrain data into RAS Mapper in part 2, set up the geometry in part 3, entered boundary conditions for our flow file in part 4, and that brings us now to the plan. So in this part 5, we'll link up the geometries that we developed in part 3 with the flow file that we saved in part 4. And we'll save 2 different plans, which we'll then run. And then in the next part 6, we'll have a look at both sets of results in RAS Mapper. So looking back at our schematic view of the file setup here, as before, I will link to this PDF workshop guide, which includes this image from back before I tried putting it into dark mode like you see here. But if we just look at the setup that we've got an existing and project conditions geometry, which will link up under an existing and project conditions plan file. So if we just focus on the files that we have now, we've got an existing conditions geometry, which is Disneyland.go1, same file name for all of these with different extensions. It's a project geometry go2. They link to 2 different terrain files, but they link to this same land classification file where we customized the Manning's roughness. And these are going to be connected to the same unsteady flow file UO1. We'll call it Disnami, the Disneyland Tsunami. And we'll have these 2 plans then to compare against each other when we get to the end of today's session. So the plan file sounds fairly simple. All we're doing is kind of linking things up, but it also covers some really important steps. So you just got to remember that HEC RAS will give you beautiful results, even if the settings you pick in your plan file make the model just absolute bunk. So the settings that we assign in this file can make the difference between a reliable model and just a totally meaningless concoction that might look good on screen. So let's open up the command window. There are 5 options for us for running plans in HEC RAS. These are the same 5 buttons that we were just showing. You can see them grouped together here, but there are also the same 5 menu items available to you to choose from under the Run tab here. So either way, it'll take you to the same place. We'll be using the buttons today. So the first two that we'll talk about are the steady and unsteady plans. And these correlate to the same steady and unsteady flow files that we talked about in the last part. So he's either doing the dance on flat ground here in steady mode or on the rising limb of a time series hydrograph here in unsteady mode. This one really could include the same time series function or the function of time in parentheses under unsteady mode here. This next one is sediment transport, and that one goes along with this quasi-unsteady flow file here. Now, we're not going to cover any of that in this series, but there are some on-demand HEC RAS sediment transport classes, which I'll link to below if you want to try it yourself. This one here, this next one is water quality, and as I understand, that's not supported or updated and is only there for legacy models so that you can compare to something that was done in the past. Finally, we've got this hydraulic design one, which is 7 different tools. If you look under type here, you've got 7 different things you can do with this. This one does get updates, but as I understand, some of them aren't current at the moment. Bridge scour, for example, isn't 100% compatible with the latest federal highways guidance and methodologies. I'll just post a link to some bridge scour discussions below, and in that one, some HEC developers comment on what's in the works to bring it up to speed. So again, we're doing a running wish list of items for future versions, and I guess that would be one thing I'd suggest. I get a lot of people asking about water quality tutorials, for example, and generally I just point them to other software. So my tip here, number one, is to put some sort of warning or caveat on the tools that aren't updated or current, because I think you can get into the documentation and find some disclaimers there about it. But I think the warning should be right up front, maybe a pop-up that you can't get past until you've clicked through the option that tells you that it's out of date. So before we open a plan file, let's make sure all of our other files are ready to go first. Now you can see that our live geometry here is the project conditions geometry where we last added some structures to it. So I'm going to take that geometry and save it back over the top of the existing one so that I don't have to redo the boundary conditions there. So I'll open up this geometry here. This will be the one with the bridge and culvert in it. I will go File, Save Geometry As, and now I will save this one right back over the existing conditions geometry, and that's going to prompt me to overwrite it. I'm going to say yes, and now I've got 2 identical geometry files. Now I'll still need to make a couple of changes to this to make it the existing condition, but let me just set everything else up first. So I'll keep the flow file here, the live flow file, which is going to be the active one that you see here. I've now got G01 and U01. This is my dirt and my water. And now we're going to go ahead and open up the plan file. So this is our running man over the hill. So in this case now I've got existing and tsunami breach as my geometry and my flow file. Before I do anything, I'm actually going to do a save. Now, just like with the flow file the first time around, save and save as are going to be the same thing. So if I hit save, it's going to prompt me for a name here. I'm going to go ahead and just call this Disneyland Existing Flood. Now, you might not know at this point what other runs you might end up with, so it's a good idea to already think about that up front because you want this title to be distinguishable from any others. So if you already know you're going to run different roughness values, for example, you might want to include something about the roughness here or anything else that you might want to change between runs. Now, when you're entering a title, just like all of the other titles, you only get 40 characters. So you have to be a bit careful about this. Before I hit OK, I'm actually going to copy this to the clipboard. So I'll highlight it here. I'm going to hit Control C. And the reason I do this is that when I do hit OK here, it's going to prompt me for something called the short ID. Now in the short ID, I'm going to hit Control V to paste in exactly the same name. What's really odd though is that the 64 characters that you get for the short ID are actually more characters than you get for the long ID. Now, I'm not really sure why the prompt tells us 16 characters is the recommended limit. You can definitely exceed that without any issues. But a lot of people try to make these different. And this is just my own personal preference. But I have a hard enough time keeping track of my geometry and flow file titles. If I then add 2 plan titles, a long one and a short one, and they're different from each other, it's just more to keep track of. And you don't really gain anything by having a longer title since it actually has to be the shorter of the 2. So I guess tip number 2, if we're doing a wish list here that we're tracking, would be to change this label here from short ID to just say label. That way everyone understands what this short ID is actually used for which will be the labels that this plan will actually get in RAS Mapper. Because once we look at the results, this is what's going to show up as the identifier in the list of results. It'll show up in every legend for any charts we make, and even the Windows folder name where the results files are going to be stored. Now, one warning is that even though you can change both the title and the short ID anytime you want using file rename here. So I could come in and rename this to be something different. The short ID won't actually get applied to the results unless you rerun it. So the reason I mention this now is because you want to be really careful with this. If you start calling this test or dummy or plan 1 or plan 2 or whatever it defaults to just to get it running, and then later on you decide that you want to keep it and give it a clearer name, this original name will stick to it, including the folder names for the results until you rerun it, which could take hours and hours depending on your model setup. So even though this tip applies to RAS Mapper, this is where you actually enter the title. And so I'll give this tip here, which is to automatically update the short ID everywhere live so that you don't have to rerun it to be able to see the new title. Now, harping on the same thing that we've said with all of the other file types, I think this is the last place where we have this description option. I'll say again, never leave this blank. So we've done this with the project, the geometry, and the flow files, but I think it's especially important for this one. I have enough trouble remembering the purpose for all of my different plan files, today, right now, when I'm working on my own models, but it gets even worse when I open my own models later on. And then if somebody else puts together a model that you're then working on, a lot of times you'll have no idea which plans are which ones were just test runs, which ones are sensitivities, which ones are supposed to get used and transmitted. Without a clear description here, it's really hard to tell. And this really all needs to match your log files inside the subfolder, so be sure to keep that current as well. Since plans just link together dirt and water, the geometry and the flows, I like to include something about the dirt and the water here. So even though I'm not being all that descriptive here, I'll just put in existing conditions, Disneyland flood, it's got a tsunami and a dam breach, and this will be the baseline sensitivity. Maybe later on in future series, we'll talk about additional sensitivity runs. So I'm going to call this the baseline, and we can replace that with any other sensitivities here to try to keep it all straight. You'll quickly run out of characters in the title if you try to say everything about a plan that might differentiate it from the others. Like if you mention the roughness coefficient and everything else, you might need some of your own codes for this title. So if you do that, high N or something like that, be a little more descriptive here. Give everybody a decoder to explain any parameters or changes in detail, because you're probably not going to run out of characters down here. Now, I do harp on this a lot because I've got a lot of models where I've maxed out the number of plans at 99. And I guess that's one more tip I should mention. You only get 99 plans. If you hit that max, it'll just freeze up on you and won't even tell you why. So my next tip is to increase that number, or at least give you a warning when it's been exceeded that you got to start deleting out some of your other plans. Okay, so now we've got a title, a short ID, and a description. We'll hit all of these other settings in a bit, but first, before I forget, let's make sure the geometry here is what I've said it is, and in this case, it's not. The only difference in our case is that the project condition included a bridge and a culvert. So I'll go ahead and delete those out here. So I'm going to save that. That changes it from maroon to black. Now I've got this existing conditions geometry. I'll zoom in here and show where that's going to differ from the project condition. And that's right here where we have these structures. So I've got a bridge here and I've got a culvert, and those are not supposed to be in the existing condition. So I'm going to go ahead and delete those out. Now, deleting things, there are typically two ways you can do that. I'll do both of them here to show each one. You can click on it and delete the connection. Do you want to delete the bridge? Yes, that's gone. The other way, again, if you want to see a list of everything that's in your model, you can go under the edit delete command. And even if you're not going to delete things, sometimes I come in here and just look at what's in my model and you'll get a full list of that. So under the connections here, I've now only got one. I would have had two if I did this one first. You've got to move it over here to see what you're going to operate on. You could select from whichever ones you want out of this list. If you had more than one, I move it over here. I say, okay, now I'm going to save this again. And now I've truly got an existing condition model that doesn't have any project features in it. Except you see the terrain here. The terrain does have this berm in it, which should not be in our existing condition either. So if I exit out of this, we'll have to go into RAS Mapper to change those associations. So I'll zoom back out here to show our project area. And what you'll notice is that when you do a save as on the geometry, it's going to save all of the previous associations that you had. So whatever I had here under project is going to also be linked up here under existing. So if I go here to manage these associations, you'll see here that it's exactly the same. So I had existing and project. They're both linked to project. I need to take my existing and link it back here to the existing condition. Now, what I'm noticing here in my list is that it's not very clear. Sometimes it's worth doing a little more organization here to make sure that things are coming up in the right order and to distinguish these a little more clearly. So for example, I had two different terrain data sources. One was all points, and then the other one was just the ground points. And so what I'll try to do here is to put them all together. I'll go ahead and move this one up to the top. So I can right click here, and move this up this way. And now I've got existing and project next to each other. And these are for the ground points. Now, these other ones were all points. So just so I can keep all of these straight, I like to put things in the same order. And what we had before was these all points. This is the project, the existing, and all. This one right here, I didn't know it at the time. I didn't know I was going to pull both of them in. So I didn't actually differentiate whether I was using ground or all. So I'm going to right click and rename this one, this layer here, and I'm going to call it Disneyland DEM ground so that I remember which ones I used for this one. So when I hit OK, I've now got a new name for this one, and it has renamed all the rest of these files as well that are associated with it. And so now what I'm going to do is move this up to the top here, and we'll put these all in the same order. So I'll take the ground point here and move it down one, and I'll take project here and move it to the top. So this way I've got my original data here, which I might modify to put in some corrections for the existing, and then modify again to put my project conditions here. I've got all points here, again, the original with existing and project, and then I've got my individual files here before I've stacked them all together. So sometimes I've got projects with 40 or 50 of these terrain files. And of course, you always start out with just one terrain file, and then you add one at a time. And for a while, it might be clear at first which one you're working on, which is which, but it can very quickly get overwhelming. So I do recommend cleaning this up whenever you can, while you can still remember what everything is being used for. So now that these are in order, I'll see them in order when I go to these associations. So when I go in here, back to geometry associations, what's happened is now that it has renamed some of the files that these refer to, it thinks that these are missing and can't actually find them. So I'm going to close back out of this. Actually, there's one more I wanted to rename here just to distinguish between the source data that we've moved here, and that's this one here, where if I rename this layer here, the new terrain name to ground, then that will be a little more clear as well. So keep in mind, this has renamed these geotiff files, and if I've cloned that and it's gone into a different layer here, then that can cause me some problems. So I'm going to move this one back up here so that they're in order. And so I move it one more up. Now I've got all and ground right next to each other here for the NOAA data. You can see the project conditions berms here. When I turn them off and go to the existing condition, you can see that I've got those break lines in the geometry. So the source data and the modifications are still here. There's no need to worry. But remember, these are virtual clones. And when I turn on the one that I renamed, you can see there's still data there. The clones just can't find them since it's trying to look for the old name instead of the new name, but we still have the data. So this is going to take a couple of tricks to fix up, but if you try this yourself, maybe it won't be as intimidating when you run into this in your own models. And of course, making this process easier would be a big wish list item, but I'm going to save these tips for the next part when we're actually focusing on RAS Mapper instead of the plan, which is actually today's focus. So others may have some better workarounds here, but my hack is to copy this modification layer back to the original and then get rid of both of these. So I'm going to copy this one back down to Disneyland ground right there, the DEM ground one. So now I've got that same modification layer, which we had here for the levee and the berm and the falcon. That's now sitting here under the ground. I'm now going to get rid of these ones here. And I've got two options here. I can remove the layer, or I can remove the layer and delete the source files. Now in this case, when I do this, it's kind of scary, but keep in mind, I'm only deleting the HDF and the VRT. I am not actually deleting the geotiff that this was cloned from. So I'm going to get rid of this one so that I can use that name again. And again, on this one, I'm going to do the same thing, remove this layer and delete the four source files. So this is going to be permanently deleted, a scary message, but that's okay. I've now got the ground file here, and I'm going to clone it again. So I will clone it once here as a virtual copy, and I'm going to call this one existing. which is now going to come right back down here on the bottom. I'll move this back up to the top so that I can keep the order clear. And again, it's got modifications that I'm not going to use here, so that I can do it again here and clone this layer, which I'm now going to call the project layer. So I've got this one here called project. And again, I only wanted for the project file, that's the only one I want to have these modifications. So I'm going to go ahead and delete the modifications out of the other ones. So I'll move project back to the top here, move it up there. I've got project, existing, and the original data here, but I don't want these modifications in this one. So I'm going to remove this layer here. In this case as well, I'm going to get rid of this one, remove that layer. And so now I've got the ground layer, the existing, and the project. And so these ones now should have some data in them. Just to clarify again why I've got ground and existing exactly the same here. I'm just doing that for the purpose of showing that sometimes you pull in your terrain file as the source data that you've got, and in order to make it reflect the existing condition, you'll have to make some changes. And we could have done that. I think we didn't. We deleted a few of those changes that we were making to try to have some corrections. At this point, these are just exactly the same file. But our difference here that you'll see under the modifications is when we start turning this on, now we can see the differences here where we've got some of the project features. And when we turn them off, I like to have the project on top so that I can see the difference here. I'll go ahead and double click on both of these and update the legend with the view, because you will lose any settings that you've made, any customization of these parameters here. And so now what we can do is turn this on and off, and you can see the difference. So I think we're all good. I've got these things now all cleaned up. That's a bit convoluted. And again, I had forgotten about some of these issues. I could just, again, delete this out of the recording and say, just do this right from the beginning. I mean, it would have been a much better approach to just really think about what you want to call these when you're first setting it up. That's why I do make such a big point about not just using the default terrain 1, terrain 2, or the names that it'll give you automatically. Do try to keep this as clear and consistent as you can, but I recognize that most of the time you don't even know what you're going to have in here at the end when you're first starting a project. And so I did want to show just briefly what you need to do to be able to organize this because of some of the limitations at the moment in renaming clones, or rather renaming the source files that the clones are based on. It can cause you a bit of grief. So with those said, let's go back to the geometry associations and now see if we can find these ones. It's still now going to link to existing in project, which it couldn't find before. I deleted these and then added them again, or created new ones that have the same name. It still remembers that that's what it wanted to link to. So again, we've got the same Manning's N layer, two different terrains that they're linked to, two different geometries. Let's go ahead and save this. We'll get out of this and go back to our command window. So we've got an active P01 plan file. That's the existing plan. We also have an active geometry file, G01, also an existing condition. I'm not going to save the project condition one quite yet. I won't set that up until I've made some changes to the settings in the P01 file, and that way I'll save right back over the top, similar to what we did with the geometry. Now, before I open this one up for the plan file here, I'm going to go back to the geometry first. Because we've made some changes, it's generally a good idea to go in and check whether your terrain associations have been made correctly. Again, I can do this by using my middle mouse button to zoom in, or the wheel to zoom in. I can't pan with that one, but I can hold shift down and left click and move around here, or I could use these view commands up here. So again, a little bit different than RAS Mapper, and it's a little frustrating to go back and forth sometimes. That will be all in the same interface going forward, as I understand. So what I can see here is that my existing terrain file has been recognized. If I saw something here that did not reflect what I wanted to see, you can always use this map button right here to turn it off and back on, and that should at least wake it up to make sure that if you see something that's different here, that indicates to you that you'd need to go back and make a change in RAS Mapper and make sure your terrain associations are set correctly. So I'm going to exit out of the geometry now, and let's open up the plan file using button number 10. So this is our unsteady flow analysis. This is Running Man up and over the hill. Let's first start by picking which programs we want to run. So of the 5 of these, we really only need 2 of them. Now, for this first one, I know we're bouncing back and forth a little bit. I am going to look back at RAS Mapper here again and show that there are places where you can do this before you even get into the plan file. So I'll move this window back here under the unsteady flow analysis so you can see this geometry preprocessor. If I took a geometry here that was on and I started editing this, what you can do then in your perimeter, you can already get it to do the preprocessing before you ever get to the run command. So if I went in here and right clicked on this perimeter and got its properties, you see this thing here, compute the property tables. We could go in and do that and have that all done before we even get into the run command. And that way you can go in and have a look at, where it has cut its sections and what some of the properties of these individual computation cells would be. I'm not going to do that now, so I'm not going to save this, but just wanted to show you that this is something that can be run in advance. And this will only run when there are changes to the geometry. If you've already run a plan before and you don't have any changes that have been made to the geometry, you wouldn't necessarily need to run it. It'll do the check anyway, so I always toggle this on. For this next one, you definitely will need number 2 on. It won't do a run. It won't actually do any simulation at all unless you have this on. That's for 1D and 2D. We are not running sediment for this, so I'm going to leave number 3 off. Number 4, the post processor. Just out of habit, a lot of people just turn this on. It really is only for 1D or combined 1D, 2D models, but out of habit, I've just left this on in case you might add something to it later on. Now for button number 5, this floodplain mapping, I see a lot of people turning this one on thinking that they won't be able to see a map of their floodplain inundation without that, but this one's a specific format. It's usually only used if you want to batch up a bunch of preset output formats for HEC Watt. I think there's a couple of other programs that would use this. I usually just leave this off. It takes extra time and space on your disk to be able to do this, and I haven't used it, frankly, myself. Now for the next part with our simulation window, HEC RAS has actually already picked a starting date and time. If we go to the flow hydrograph that we're using here, you can see that it's actually picked a medieval date for the year 1000. You could assign a fixed start time to this initial time step right here, and then your simulation window could run any part of that time series instead of having to go right from the beginning. For the simulation window, though, it used to default to, I think, 1900 or maybe 1999. That would get confusing if you're running a hypothetical event, because sometimes you might mistake that for an actual event that happened in 1999. So I'm sure we wouldn't be modeling something back in the year 1000 from 1000 years ago, but I'd still suggest this default should be changed, because Excel can't handle dates before 1900, and it still actually mixes up the leap year from an old Lotus bug. So I always stick with hypothetical synthetic events for the future. So for a lot of time, I used to use the year 2020 as my default, thinking there was no way I was still going to be modeling 20 years from then. I've had to change that now to the year 2050. So I always use 01 Jan 2050. Again, use your own preferences here. You can use whatever you like. I also don't like the ambiguity of having 2400 on one day be the same as 00 on the next day. And so I always just started at midday. Date formats are very, very important. And just as a warning, because of dates and decimals in different regions, some Windows versions can't actually run HEC RAS without changing your regional settings here. And that can be a bit of a pain. I keep a running list of some of the ones where we've done courses, but another tip, it would be great if all the Windows regions could get that just updated automatically. Now for the ending date, I'm just going to make this a 24-hour run. So I'll choose 02 Jan 2050, and likewise, I'll do it midday. So this is going to be a 24-hour simulation. And again, just to reiterate, if you try to run HEC RAS and you're outside the US and it just won't run, you may want to go into these Windows region settings here. I've got mine set to Australia. That works just fine. Sometimes we go to these classes where it just seems arbitrary, like side-by-side regions. We'll have Bosnia and Serbia, and one will work and one won't, even when they're using the same date formats in their own settings. And so you may want to just change this to English United States and just give that a try if you're having any troubles. Now here under computation settings, this is the number one thing that messes up more models, I think, than anything else. A lot of people, when they're first picking up HEC RAS, they'll just leave these as they are at the default values. And we'll cover what these should be set to in a few minutes. But one more tip in the meantime is just to default to a smaller time step, or maybe an adaptive time step here. That way, if things end up running too slowly, you just adjust other parts of your model, like the coverage extent or the cell size, but at least you'll have a stable model. So I'll come back to that in a second. But for these other settings, I like to drop them all. The defaults are for very large models that will be running for a really long time. You'd want to make sure you have enough results to smoothly show what's happening. So I'll change all of these to say a 5-minute interval. So I'm going to take this one here, this one there, and this one here, and change them all to 5 minutes. Now, just thinking about a video, a high frame rate might be about 40 frames per second when you're watching a movie. I think the standard frame rate is maybe 24. But say you wanted to make an animation out of your HEC RAS results. If you wanted to see what's going to happen in HEC RAS and put these into some sort of animation, how long are people going to actually watch that? Nobody's going to pay attention for 3, 4, 5 minutes of your video. If it's 10 seconds, it might be too quick. So I'd say there's probably this sweet spot of maybe 20, 30, 40 seconds for your video animation. So looking at our 24-hour simulation window here, if I wanted to have, say, 10 frames per second for 24 seconds, I guess I'd be wanting to make sure that I had inundation extents every at least 6 minutes. I guess that would give me 240 frames for that 24-second video. The thing that's a pain is if you guess this wrong and you get really choppy results, you've got to rerun it. So I usually try to guess a bit high on this one. It doesn't change your run times too much, but it can definitely increase your output file size if this gets really, really small. The differences between some of these settings might be a little more clear once we're looking at results, but do make sure that if you choose one of these intervals here, like this 5 minutes, if you go too coarse, you might miss the peak of a hydrograph, for instance. So you've got mapping, you've got hydrographs, and you've got detailed output where it's going to save some of these results for you. And anything in between won't be saved. So if you want to change this later on, you might have to rerun it. Now keep in mind that these settings here have to be intervals of the computational interval. It can't write output for a computational time step that wasn't actually computed, if that makes any sense. So let's talk next about what this number right here, this computational interval, should be. To make that decision, or at least to take an initial stab at it, we need to dive into the Courant number. So if you already understand Courant numbers, you might want to skip ahead to the next chapter, but this is one of the most critical concepts for any modelers. Could be 1D, 2D, 3D, could be CFD, thermodynamics, space travel. Doesn't matter what you're modeling. The concepts for the Courant number are basically the same. Now, hydraulic equations can get very complicated, like when you look at Navier-Stokes or the St. Venant equations. The Courant number usually isn't so bad, but here is an excerpt from a NASA article about the Courant number. I wouldn't even know where to start if someone asked me to review something like this, because for myself, I've got to admit, I get intimidated by equations like this very quickly. So when I'm teaching classes, I like to keep things pretty basic and just keep the equations to a minimum. But there are a few equations that I think we do have to cover to some degree. So far we've only covered some really basic ones, like volume equals the discharge rate times time. So volume, V equals QT, or Q, the discharge rate, equals velocity times cross-sectional area. So Q equals VA. Those seem pretty simple, but to enter our first guess at the time step, this is the equation that we'll actually need, the Courant number equation. These are just transcribed from a bunch of different software manuals that all refer to the same thing, but it starts out looking a little more complicated than these other two that we just talked about, but we'll see in the end that it does simplify into something that really is no more complex than these ones. So in short, the Courant number is just the number of cells that water will move in one computational time step. So let's say we had an area where flow is just moving along here, and this will just be a floodplain that we'll show here. But say we gridded this up, and now we want to model this with rain on grid. So flow would be transferring between all of these cells. The number of cells that a drop of water would move each time the computer does a computation is the Courant number. So we spent a whole hour with Chris Goodell and some NASA engineers, some professors and some others talking about the Courant number in this Australian Water School webinar. It's number 135 if you wanted to take a deeper dive into this one, not just the Courant number, but we talk about Euler, St. Venant, and others as well. So back to these equations though, even though it's relatively simple, this equation still has some Greek letters in it. And even though that tends to scare me, there's no need to panic here because the only Greek letter that we see here is actually delta, and delta is just the change. So let's break down these terms. C equals V times delta T over delta X. Well, V is the velocity, and that includes wave celerity. So we'll hit that in a little more detail when we're looking at the Froude numbers and the results. But the delta t, the dt, that's just the computational time step. Dx, delta x, is the computational grid size. So if we get rid of these deltas and move things around, we've basically got c equals vt over x. My old high school physics teacher used to say, here's an equation that's as easy as dirt. So in this case, d equals rt, distance equals rate times time. Now that should make sense because it gets thrown into all sorts of the story problems that we all feared in school. You know, a train is leaving this station at this time or arrives at this station here. But it does come down to a very simple concept, which is if you drive at a rate, say, of 86 kilometers per hour, and you do that for 1 hour of time, you've of course traveled a distance of 86 kilometers. So all we need to do to get back to the Courant number is to replace this d with an x, and we replace the r with a v, and now we've got x equals vt. So if we wanted to swap those around and solve this one for t, we'd have t equals x over v. So if we take that to the other side, we can swap it around again and swap the v and the t, and now we've got v equals x over t. So we've now solved this one 3 different ways. So it's really just saying the same thing with 3 different forms. Now to pull this one into the Courant number, let's go ahead and go back to our x equals vt form of this one, and let's put the Courant number into it because x is, of course, short for 1 times x. So I can replace that with a 1, and we have vt over x equals 1. So then if our goal is to make the Courant number 1, then c equals vt over x. And so we get rid of the 1 there, and we really want our max c to be 1, which means we want the max v and the minimum x to result in something that does not increase the Courant number beyond 1. Now you can go a little bit higher, but that's going to be our target for the first couple times we work through this equation. So again, here are the 3 forms of it, but the problem is that we have to know 2 of these 3 variables to determine that third, and when you're starting a model, you don't necessarily know the v or anything else about it. What you do know though is what your grid size has been, because we've already set that up with our geometry. So if we don't know the v, we might have to estimate it. And so if you're going to work with a fixed solution where you have a fixed time step, you'd have to estimate what that velocity is going to be before you even run the model, and then you would iterate from there. Now we have an option, an adaptive solution. It's a variable time step within HEC RAS where the computer does that work. We'll want to get familiar with both approaches, but in the meantime, what do we do for our initial guess if we're going to go with a fixed time step? Here's some guidance from the 2-flow manual. This one says take the time in seconds to be 1/2 to 1/5 of the cell size in meters. So the way the units work out here, that's basically an assumption that the denominator is the maximum velocity. So that means that that would be 2 meters per second for using half the grid size, or 5 meters per second for using 1/5 the cell size. So typically in a stable model for a river, you might expect your maximum velocities to be somewhere between 2 and 5 meters per second. So this sounds like some pretty good advice if you're targeting a Courant number of 1, which seems to be a pretty typical target we might want to have. So the HEC RAS manual says you can go up to 5 with the Courant number. Now, I definitely don't like to go that high, but I'll link to the documentation page that has these equations in it about the Courant number. So again, back to our floodplain. Let's look at what happens between time steps if we use higher Courant numbers. If the Courant number is 1, the model does a computation when it starts, and the water does another computation when it gets to this next cell over. And if we then double that Courant number to 2, you'll see that we do 1 computation there, and the next computation, it has skipped a cell between computations. If we double that again to 4, now the model has no idea what the water encountered as it moved from here to here. We just skipped a couple of cells, and by the time it runs that next computation, the water's already there. So once we look at the results, we'll show you some cases of what happens and what the results look like when the model just can't keep up with itself as it's trying to work everything out because that time step is too coarse. Now in a classroom setting, hopefully this isn't one of my classrooms, but you never know, we'll make each desk a computational grid. And then I'll walk around or jog around or run around, and we clap at 1 second computational intervals as we move quicker and quicker. So we start at one desk, 1,000, 2, 1,000, and we do computational intervals every second. We move quicker and quicker, we start skipping desks. So going back to our project, we need to think about what the velocities would be in the vicinity of our area of interest, but also what the velocities would be elsewhere throughout the model. And I've entered some really big flows here. I think we went up to 8,000 cubic meters a second in the Santa Ana River. So those velocities might be really high, but we're out here in a floodplain. So maybe 1 meter to 2 meters a second might be fine. But likewise, we're bringing in a massive wall of water, I think 47 meters high here at the ocean. So we might expect some really high velocities at the coast. So in the area where we've got the smallest grid sizes, I had a 40-meter grid size here. If we had a 1 meter per second velocity, let's think about what this equation would give us. If we had t equals d over v for a 40-meter grid size, t equals d over v would give us 40 seconds for a time step. Or if it was 2 meters per second, it would give us 20 seconds. So I guess let's just split that difference. And for now, for our initial guess, we'll just call it 30 seconds as the fixed time step. So, well, for a quick thought exercise, temporarily I put in this refinement region right around the Millennium Falcon, and we had a 5-meter grid size there. I deleted that, knowing that would really blow up our time steps. But think about using that same equation, and you see that we would be talking about at least 8 times the runtime here, because we would be cutting our time steps into 1/8 their original value. Because we would be cutting those time steps into 1/8 the value that we would need if we had 40 by 40 meter grid cells. So now let's talk about variable time steps, and we can get to the variable time steps in 2 different ways. So I'll pull my unsteady flow analysis window back up here. Let me minimize this to just keep this nice and clear. If we're looking at the variable time step, we've got these 3 dots. It always makes me nervous when I see things in maroon here, so I'm going to save that and just make sure we've got everything saved that's the latest. We've got 3 dots here, and that's supposed to take us right to the variable time steps. Only it doesn't. It goes to the general tab. I think there was a version when it used to actually take you to advanced time step control. So this ... right here is supposed to go to advanced time step control. You can also get there. So when I click on that, see if this looks familiar. When I cancel this and go back to options, computation options and tolerances under the plan menu, it takes me back to this same general tab, and I can get right back there to the same advanced time step control. So having a look at the tabs across the top here, we're not going to hit all of these. We've got the general tab. We'll talk about a couple of these settings here down the road. We've got 2D flow options. We will talk about these in a second as well. Pipe systems is a new one that just came in with version 6.6 a few months ago. 1D, 2D for some coupled models. We've got the advanced time step controls here and the 1D mixed flow options. So we're going to focus on this one for right now. Instead of the fixed time step, which under a basic method would give you 1 minute. That's the default here. If I wanted to change this to adjust this to base the time step on the Courant number, let's just start here with a Courant number of 2 and talk about what that means, and then use 0.5 for the minimum Courant. And then for now, I'm going to put in 5, 5, and 5. That's usually what I always start with. But would this make sense? So let's talk about some of these numbers. I sometimes will reduce the maximum Courant to 1, but when I first start out, I'll have it up at 2 just to keep the run times down. If I went down to 1, I would actually need to change this to be less than 0.5. It needs to be a factor of less than 2. I don't think it would be a big deal, but you see some odd numbers here. When somebody does 1, you'll see this one be 0.045 or something like that. You may as well, if it's stable at 0.49, you may as well just allow this to be a factor of 2 instead of less than 2, so 2 or less. So let's talk about the other numbers here. This one prevents oscillations. It prevents it from bouncing back and forth by forcing it to violate the criteria a certain number of times before it makes an automatic adjustment. You do need to be a bit careful here, because sometimes HEC RAS will pick a time step that's really coarse, say while a reservoir is filling, and then when it breaches, and by the time it catches itself and gets something reasonable, that initial breach wave is already gone. So in those situations, you might want to look at doing some manual slicing. We're not going to talk about that too much here, but the main thing I wanted to focus on is the fact that you don't want to be up against one of these numbers here, because these represent the bookends that HEC RAS is going to test. And if you're up against this, HEC RAS is not going to be allowed to keep factoring these. So if I use a 5 here and I have this one toggled on, this gets grayed out. So it almost looks like it's not going to be used. But let's go back here. I think we said let's use a 30-second time step. So I'll change this one to a 30-second time step. Watch what happens here now. Those numbers have changed. So basically, instead of taking a 1 minute time step right there, see that went up to 32 minutes. Even though it's not using this anymore, when I go to 30 seconds, it has already made this adjustment. So essentially what we're doing is we're taking whatever number is in here and we are going to double it 5 times. So 30 seconds is half a minute. So we double it once and we've got 1 minute. Twice is 2 minutes, 3 times is 4 minutes, then 4 times is 8 minutes, 5 times 16 minutes. Okay, so same thing with cutting it in half. We start out with 30 seconds, we go to 15, then 7.5, then 3.75, then 1, almost 2, and then just under 1. So that's the 0.94 seconds. So this is the range in which HEC RAS will test out different time steps that it can use. But let's talk about what would happen if we use this adjustable or variable time step. I was just looking at, and picking the 30 seconds, I was looking at where I've got the smallest grid size. But if I use this, it's going to check everywhere in my model, including the areas with the highest velocities, which would happen where I've got bigger grid cells. So I think we had a 100-meter cell size in these areas where we had the dam breach hydrograph coming in. So that's going to have some very high velocities. Let's call those maybe 5 meters per second. So if I had 5 meters per second right up in here where I had 100-meter grid cells, what's going to be worse? Where I've got finer grids or where I've got the highest velocities? So if that was a 100-meter grid size there right at the breach location and we had a 5 meter per second velocity, then that would give me 100 over 5. It's a 20-second time step. So maybe that would be my worst case and not around the berm. But we might still be pretty close to the 30 seconds. Likewise, out here, I had a 100-meter grid size and say I had a 5 or maybe even a 10 meter per second velocity when this tsunami arrives. Maybe you'd be looking at 20 seconds, cut that in half to maybe 10 seconds. So that's still not too far off. Think about, though, what would happen then if I looked a little closer at my culvert right here. Now, think about how culverts can constrict flow, especially when they go under pressure flow. Velocities at the inlet and outlet could be much, much higher than the velocities out here where I've got some flat areas. So if I ran this with a variable time step, the run times might go way up, and that would be for the entire model, because every single cell in your model needs to run at the time step that's appropriate for this one cell right here where I've got the culvert location. And so sometimes I've seen models where adding just one culvert to the model can make the run times go up by 10 times or more, even if the rest of the cells stay the same size. So now let's talk about the uniform cell size for the entire model. There is a rule of thumb that cutting the grid size in half increases your runtime by 8 times, so almost an order of magnitude more. Essentially, that factor would be 2 times 2 times 2, so 2 cubed equals 8. To nail that concept down, though, maybe we go back to the grids that we were looking at in part 3, and then we'll just include the computational time step, or an estimated computational time for each of the different resolutions that we plotted. So let's say we started with a model that covered an area measuring 10 kilometers by 10 kilometers, so 100 square kilometers. And if we used 100 meter by 100 meter cells, that would give us 10,000 cells. So in the red here, if these were our cells in the Santa Ana River, and I cut a cross section right across the top here, we would basically have a single water surface elevation computation for this river level. So you would have no super elevation computed. If there was a bend, you wouldn't see higher velocities on the outside of the bend. You wouldn't see any variation at all across the cross section. Essentially, it would behave like a 1D model. So let's see what happens if we start decreasing the cell size. If we had 90 meters by 90 meters, or let's go to 80 meters by 80 meters. In that case, just going from 100 meters to 80 meters on the computational cell spacing doubles the runtime. So we had 5 minutes before, this would give us 10 minutes. If we keep going, you can see what happens here. We'll get more and more computational resolution across the top here. By the time we get to a 30 meter by 30 meter computational cell, we've got 3 different water levels that would be computed here. So you'd start to be able to see some of the variation inside of the river channel. But that comes at the trade-off of the cost of computational time. We've now got 3 hours of computational time. Let's take it a little bit further. If we had 20 by 20 meter computational cells, we get a little bit more, but now we're up to basically all day long, 10 hours worth. So that's maybe not a big deal. If you hit run when you leave the office, it'd be done by morning and the computer would do all the hard work. But now this next step is the one I really wanted to stress, going from 20 meters to 10 meters. So you can see we've got lots of resolution here. We're able to define any variations across this cross section really well, but look at what happened to the model runtime. So if we have to wait 80 hours for results, I guess you could kiss all of your sensitivity runs goodbye for now. You won't even see your initial results until next week. So that's a 2:2 ratio for the grids. So we've got twice in the X and twice in the Y. So if we go back here, each 20 by 20 meter cell, if I take and cut that in half, now we've got 4 10 by 10 meter cells inside of it. So there are 4 times as many cells, but you'd also have to run twice as many computations when you cut the time step in half to keep the Courant number the same. So I think it's really important to recognize this big trade-off because, again, every single time you cut the time step in half, you basically increase your runtime by a factor of 8. Now, keep in mind, no matter what computational cell size you use, due to the subgrid sampling capabilities in HEC RAS, it's still going to pick up the terrain points at the underlying LiDAR resolution. So in our case, we had a DEM that was 2 meters by 2 meters inside of our terrain file. So you get 5 actual computed depths across each computational cell here. So when we look at it in 2D, we'd have 10 meter by 10 meter cells with 2 meter by 2 meter LiDAR. You would essentially have 5 times 5 or 25 LiDAR cells for every single computational cell here, and you will get a depth computed at every single one of those LiDAR cells. So that means even though you have a 10 meter spacing here, you're going to pick up the underlying LiDAR depths off of this single computed water surface elevation. Once it triangulates it, it's going to pick up all of those depths. So you get a lot more resolution out of it than you might think. So if we come down here and go back to our 100 by 100 meter computational cell, now we've got 50 by 50 LiDAR cells underneath that. That's 2,500 depth points inside of each computational cell. Even if it's not based on a whole lot of computed water surface elevations, you get a whole lot of depth out of it. Now we'll cover a lot more about how RasMapper works with those results and how you can visualize those results in the final session. So taking it back to where we left off with our model settings here, just to keep the initial run times down, I'm going to end up toggling off the variable time steps that we see here, and I'll change it back to fixed. But keep in mind, this range that you see displayed right here is based on what you've temporarily put in right here as the fixed time step. But if you look closely, you'll see that it still doesn't match what you've got here in the actual computation settings. So even if you think you're getting this minimum time step of 1 second here, if I leave it on adjustable and hit OK, you still have the 1 minute there. When you come back in and have a look at the advanced time step control, you'll see that this has reverted back to the 1 minute that we saw earlier. And now your actual minimum time step is 2 seconds, closer to 2. So if you wanted this to actually change to the 30 seconds, which we computed based on our Courant number equation from the assumed velocities, that 30 seconds, if I now leave it as fixed time step and say OK, now it changes here. Alternatively, you can change it here first, save this, and then go back in, and what you'll see on the variable time steps now, if I go back to that, I've got the actual 1 second minimum that you would get by cutting 30 seconds in half 5 times. So I guess that leads us to another tip here. If this could automatically match without having to manually make sure of that, that would make things a little less confusing. So again, I'm going to keep this as a 30-second fixed time step, and I will go ahead and put that in the description here, 30-second fixed time step. If I'm not running any other sensitivities on this, then that's probably fine. But say I did want to run this as a variable, what I would then do is just make sure that this description always matches. And say I was going to run this one right here with variable time steps, I would go ahead and say here in the plan, put like a code like VT up here in the plan and in the short ID. And then here I would say that's what I'm running, a variable time step. And I wouldn't just say that it's variable. I would also say that it's got a max Courant of 2. because you might want to run some sensitivities on that. Now, again, it would solve a lot of the instability issues that pop up in online forums, or even when some people proudly put their very first HEC RAS video up online without realizing that the Courant number is actually way off. And you'll actually sometimes see things get built off of bad results that sometimes could have been prevented by defaulting to a variable time step with a relatively low Courant number threshold in the first place. Even though that could increase the run times, I think that would sure avoid a lot of the initial model crashes and other problems that sometimes get passed around for comment online. Now, keep in mind that if you are going to be using an adaptive time step, this output interval that you see here is really just a guideline, because it will pick its own computational interval based on your adaptive time step criteria, but that has to be a multiple of what's running in the background here in the output time steps. And so if you're comparing two model runs, you might not actually be looking at results from the same time step, even when you think that's what you're seeing. So let's look at some of these other options. If you go to this tab here, there are a whole bunch of very important numbers here in the options and tolerances menu. In our case, we're mainly talking about this second tab here for 2D flow options. There are a whole lot of others. Out of all of these ones here on the 2D flow options, I'm actually only going to talk about this one, number 10 here, the equation. I definitely don't want to ignore the others, but since we're going on an hour already, there's a whole 1 hour full momentum episode called Getting to Know the Computation Options and Tolerances. It's number 19. I'll link to it below. That episode steps through the mixing, the turbulence, Smagorinsky coefficients, and a bunch of other parameters that you may have never even thought about changing. Most models that I see, they keep almost everything at the default, but I do think it's a good idea, at least one time, try to go through each one of these in more detail, try some sensitivities with some of the settings, and see what happens, especially if you're in a highly turbulent or dynamic situation. Now, the problem with a lot of these, though, when you look at the documentation, is that you're basically asking yourself questions about the entire model. So I would definitely recommend reading through this whole page on the Confluence site, which I'll link to below. It asks you to consider whether you've got a couple of different situations. Like if you scroll all the way down here to where we look at mixing, it's going to ask you, do you have a little bit of mixing, a lot of mixing? Do you have a straight channel? Do you have a meandering channel? But what if your answer is yes to all of these and your model includes a little bit of everything? Then what do you do then? There are a lot of larger models that have some attributes in one place and other attributes elsewhere, but you only get to assign these values once to every single computational cell in the whole 2D area. So it's going to apply to all of them. You could hook up a bunch of different 2D areas with different values here, but nobody really likes to do that unless you absolutely have to. So again, I think the key here is to test the sensitivity to see if these changes would affect your area of interest in any way. So I'm not going to say much about the rest of these parameters, which you see here. But the one thing I will hit in this menu, like I mentioned, is number 10, the equation set. Right off the bat, though, I will mention this next tip here, which is just to default to this first full momentum equation. So it's number 2 on the list here. I'll explain why I feel that way in a second, but on a related tip, sometimes people change the default here and say, okay, I would like this one to be a full momentum equation set, and then they won't go back and look, and the next time they start a project, they won't check it thinking they've changed the default. What they sometimes don't realize is that this here, this default setting, applies only to new 2D flow areas created in this project. So if that's what it's actually doing, is applying just to this project, my preference would be for it to tell you that that's what it's doing. So say this project only here behind the default values. So there are actually 4 equation sets to choose from. I will link to the documentation page where each one of these is described below, but essentially we're just going to be taking the full momentum SWE, that's the shallow water equation, which is dumbed down from the St. Venant equation, which itself is already dumbed down from the Navier-Stokes equation. Basically, we make some assumptions about the horizontal scale being much greater than the vertical scale. A bunch of other things drop out, and we're left with this. Now, this slide comes from a 2-flow presentation that I'll link to below, but I think it lays it out pretty clearly in terms of what the different terms are. It looks a little more convoluted on the HEC RAS Confluence page, but if we have a look at that, we can see where these equations actually come from. So I'll link to these pages on the HEC RAS Confluence site down below, but if you really want to geek out on it, you can have a look here at the momentum conservation page here. You can see what we start out with, which terms are included, and then if you go to the diffusion wave approximation, you can see which terms are dropping out, and you can then find something down here that looks an awfully lot like Manning's equation, and what you'll see here is all we're considering in this case is the bottom friction and water surface terms, and then you get this simplified approach. So looking back at our plan settings here, even if you don't want to geek out on it and get into all of the background theory, I think every HEC RAS user absolutely has to be familiar with the limitations that come from the different methods. Now, the default, as I mentioned, is the diffusion wave. Sometimes when you click on this, the drop down goes away and you got to click outside of it and come back to it. But again, looking at each of the four, the default is the diffusion wave, which removes some of the inertial terms. Now, this one here, the second one, used to be called full momentum, but the name got a bit more complicated than that. This is SWE, shallow water equation, ELM. That's the Eulerian-Lagrangian method. We also have a stricter momentum here, which might be used for detailed bridge models with piers or other hydraulic structures. It's got tighter limits on the maximum Courant number than the other ones and might take a little bit longer to run. And finally, we've got this last one, which actually ought to be between these other two if we go in order of complexity. This one's a simplified version of the full momentum equation. And I guess that's another tip. If these could be just reordered by the level of complexity, that might make it a little more clear. You might otherwise assume that these are getting more intense along the way, but that's not the case. So 99% of the flood models that I see use number 2 here, and that's what we'll be applying. So I did want to cover a couple of key differences, though, between diffusion wave and full momentum. Actually, spellcheck corrected my report the other day and told me I should be calling it entire momentum, which doesn't really have the same ring to it. So back to the menu here, another tip is to include the term full momentum in these options where applicable. So back when there were only 2 options, the second one was called full momentum, and still throughout the documentation, it'll say use the full momentum equation. But then you look at this drop down and you don't know which one to pick here. Which one do they mean by full momentum? So to avoid confusion, it would be good if the documentation could specify which of these 4, maybe number them, the advice is applying to, but if it just says full momentum, then we should at least make it match here and have it say which of these are full momentum equations. So it might be worth talking about the word momentum quickly and what that means for water. Sometimes you'll hear about the conservation of momentum. So what does that mean? Essentially, an object has momentum when there is both mass and velocity. So you might have a tiny mass with a huge velocity, and that can have a whole lot of momentum. Look at this piece of metal here that's been hit by an object that's the size and weight of a pencil eraser that was fired at this metal block at orbit speeds to simulate what happens if space junk hits you out there. But this big block of metal, if it was just sitting there at the moment, there'd be no momentum relative to your own reference plane. So if you had 2 cars and they're both the same weight and they hit each other at the same speed and come to rest, they'd be all crumpled up. But what if one car hit a fixed object like this tree? It would also come to rest. So where did all that momentum go if it's conserved? So it can't be destroyed, but it'll be redirected or scattered. So if you hooked that tree into the earth, maybe you've slightly changed the earth's rotation, like immeasurably slightly. So if you think about that like a bridge pier with water heading toward it, where does that momentum go? We'll talk about the related concept of energy conservation in the last part when we start plotting out the results. But first, let's look back at the 2 choices that we have in our drop-down. Why would we pick one versus the other? Why would we want to consider full momentum? Well, according to the manual, let's look at some of the situations where you wouldn't want to use the simplified equation. So I'll link to this page below as well, but here are some of these situations. If it's highly dynamic, if there's contractions and expansions, if it's flat or tidally influenced, if you have super elevation around the bends, or if you need some detailed velocities at the structures, mixed flow. So basically, the default shouldn't be used for any of these. So what's left here? Maybe like an irrigation canal? I mean, really any situation that the default diffusion wave is appropriate for could probably be modeled with 1D or maybe with Manning's equation. If you're in 2D, you've probably got some situation somewhere in your model where the simplification wouldn't apply. So sometimes it makes a big difference in run times, so there might be an advantage there. Sometimes it'll actually make hardly any difference in the water levels, in the velocities, or in the other parameters. So if that's the case and you saved yourself some runtime, Maybe it's okay to use the simplification in those certain situations. But in my opinion, you'd always want to at least check one of your runs as a sensitivity to see how the results are affected before ever going and presenting or finalizing a model that has the diffusion wave as the selected equation set. So sometimes people will go through and run the diffusion wave and it's error-free, and then you run full momentum and there are errors. So they'll go back to diffusion wave thinking that that's a better answer. It's not. It just means that the diffusion wave just ignored the terms that are giving you problems. So let's think about what it's ignoring. Some of this might be clearer once we've looked at the flow patterns and the results, but there are a couple of terms that I think are worth considering when you're choosing your equation set. So first, maybe we'll step through the basics of force and acceleration. If you're clear on this already, just skip to the next chapter. But I think I'll have to make my video bigger for this one. So if I take this yo-yo here, and I take a 1/2 meter of string, and I start spinning it around my head, if it's a 1/2 meter of string away from my head, then both ways, that's a 1 meter diameter. So the circumference is pi meters. If I keep spinning it at this constant speed, let's call it 1 revolution per second. So I've got 1 1,000, 2 1,000, 3 1,000. Well, that gives me pi meters per second. So this yo-yo is moving at a constant speed of about 3 meters per second. So the question is it accelerating? And the answer has to do with vectors. For terrains, we've already talked about the concept of vector versus raster, meaning you either pixelate when you zoom in, like when a raster grid digital elevation model has a set resolution, or if we're talking vectors, like the triangles in a tin or the points in a point cloud, a line is a line is a line, no matter how far you zoom into it. So points are points. They are not going to have sizes or volumes. Faces won't have any thickness. Doesn't matter what zoom level you choose, there's no thickness. So that's vector versus raster. Now, in this case, we'll still be talking about vectors, but for a whole different reason. And that's to differentiate vectors from scalars. So in our case, speed is a scalar. That's easy to remember because they both start with S, and velocity is a vector. Also easy to remember because they both start with V. So this constant 3 meters per second that we talked about is a magnitude only. So we can't say it had a velocity of 3 meters per second because that's only half of what we need to say about it. To be an actual velocity, that speed has to have a direction. And in our case, that direction happens to be changing every instant. So the velocity vector has to have both magnitude and a direction. And so if there's any change in either one, or it could be in both, then that would be the definition of acceleration. So even though the magnitude of the speed of my yo-yo didn't change, the direction of that speed when it's over here on my right side is entirely opposite to the direction of when it's on my left side. So there's definitely going to be some acceleration. And what's the direction of that acceleration? Well, F equals ma. Mass itself has no direction. It's just going to be a fixed property of this object. So this yo-yo can only get the direction of its acceleration from the F. So ignoring gravity, there's only one way that this force can act on this object, and it's through this string. So if I cut this string while I'm still spinning this around my head, if we were in a vacuum, that yo-yo would just be set free. So it'll just continue in a straight line from that point forward. So when it's spinning, this yo-yo is accelerating in the direction of this string, which is toward my head, just like the moon accelerates toward the earth toward the sun, and so on. So that seems like a very basic concept, but what does that mean for water when you start ignoring inertial terms? So water, if it's flowing in a straight line, it's got inertia. You can't measure inertia per se, but it takes a force to change the direction that that mass of water is traveling in. So that's technically an acceleration going around a bend, even if the speed doesn't change. If something slows down or comes to a stop, we'd usually call that deceleration. But it's still going to be acceleration. It's just negative given whatever we've assumed the positive direction to be. If there's a tide that's coming in and going out, it's accelerating. It's not that it's getting faster and faster, which is how we typically think about the word acceleration, but its velocity, even if it's really small, changes direction. So sometimes that's semi-diurnally. It'll change direction and head the other way. And that can be a pretty significant term if you're trying to compute hydrodynamics. So when we get to a bend, the water keeps heading toward that bend. It's going to want to keep flowing in that direction unless a force acts on it to change the direction. And so it'll bank up, and with its super elevation, you'll get higher water surfaces on the outside of the bend. And that'll be just like the super elevation on a road if you get a bank turn. And so the important part for us here is that you will not see the effect in the default diffusion wave simplification. You won't see super elevation. You also won't see eddy patterns, like when it spins around. And we'll revisit that when we start looking at the results. You will only see that phenomenon show up when you're using the full momentum equation. So again, I know we're going back to high school physics for this one, but I think this is really important to consider when we start getting back into our model and selecting which equation set we're going to use. So I'm going to change this one here to what they call the original full momentum equation. It's the second one in the dropdown, and I'm going to leave all of the rest of these settings at their defaults. Even though I know I'm supposed to change some of these others, like for example, if we're going to be modeling a tsunami, it's not technically a tidal wave, even though we call it that, but if you are using a dynamic stage boundary condition where things are mixing and flows are going in and out in both directions, you probably need to have a look at the theta value, which is number one on the list here. There's a great discussion with Gary Brunner, who we talked about at the very beginning of this session, covering tidal modeling. He talks about the differences between first order and second order solutions and a lot of other really helpful modeling tips. It's in Full Momentum Vodcast episode number 21, which I'll link to below. Now, there are some people who recommend adjusting some of these thresholds and tolerances for rain on grid modeling. And some of those settings are actually in the geometry and not in the plan files. Let me open up the geometry here and edit the 2D area. You'll see some of these filter thresholds. Now, there are some modelers who recommend decreasing some of these thresholds by a whole order of magnitude for rain on grid models. The 2Flow manual actually says to do the same thing to wet-dry coefficients. You divide the defaults by 10 for rain on grid. The computations might be handled a little bit differently in HEC RAS, but I have not yet seen any official written guidance from HEC on how to customize some of these values for rain on grid. So that would be one more tip, to include some official guidance for rain on grid settings and tolerances. And that would include not just these thresholds, but also the roughness values. If you click on the question mark next to the roughness values, it'll take you to this Confluence page where we see these tables full of roughness values from Chow, I believe, and a couple of other sources. What you'll notice when you go into the help menu is that these are all channel values. It'd be great if someone could do a definitive study on this. I think there is a UK benchmarking study of 2D models, which I'll also link to below, including the HEC response to that. In that study, you'll see some rain on grid examples where some of the studies use 0.2 or 0.3 for shallow values. So not 0.02 or 0.03 like we're seeing in some channels, but 10 times higher like we talked about with the geometries and when we need depth varying roughness to get very shallow flows over very small roughness elements, which end up looking very big to the very shallow flows. So it would be great if we could get a TD or an RD document with specific guidance and study results for rain on grid, since it's being used for that so commonly now. Now, that all said, to keep things simple, I'm going to leave the rest of the defaults alone. When I go back to these settings here under computation options and tolerances, you'll see all these 2D flow options. I'm going to leave all of the rest of these the same, even though they all probably deserve a closer look. So I'm going to run this at a fixed time step of 30 seconds, which you can tell by the color here has not been saved yet in the description. And this note here actually tells me that it's going to run as a variable time step. So always check this. I'll go ahead and change this back here under advanced time step control. Make sure I'm choosing a fixed time step. When I say OK, you'll see that note go away. So always check this to make sure it's going to be running what you actually want to see. Now, if I'm going to compare different model runs, I do like to make all of my changes to one plan first and then save it as a new plan. So at this point, we've only got a P01. That's the existing condition plan file. If I had already set up the second one as my project condition, we'd have to make any changes twice, and then sometimes I forget which changes I've made, and then there's some difference between the model runs that I didn't actually intend to compare. So if I'm sure I'm done with everything now, and I want to see the differences between existing and project conditions with no other computational changes, I can take this and save this one first as the existing, and now I'll go File, Save Plan As, and I'll call this one Project Flood. So Disneyland Project Flood. I will highlight this, use Control C to copy, and when I say OK, it asks me for this short ID, which I will then replace with the Project Flood. Now, there are a couple of things that don't match, obviously. It still says existing here in the plan description. I'll change that to project. And also on the dropdown, it is now referring the project flood plan file to the existing geometry, which is incorrect. So on the dropdown, I'm going to now associate it with the project condition. And again, when you see this color go maroon, I'll say File Save, and now we know that this has been saved as the project condition. We now have our active plan file as PO2 up here. This is the project condition flood. So now we are ready to run. We can hit compute. Before I do that, though, let me just mention another suggestion. Since the equation set is so important to your model results, it would be great if we could have this compute, say, compute with full momentum, original full momentum, diffusion wave, stricter momentum, whatever it is. I guess you could have multiple approaches in the same run. Maybe you could combine that here, but I do think it would be worth including so that there's no mistake in which equation set you're using when you hit compute. Now, instead of running these one at a time, which I could do, I could run this one and then open the next one and run it. I'm actually going to close this and use this batch command, which is under the run menu called run multiple plans. Now, when I pull this up, at this point, it's pretty simple. There's just two. But again, you might have 20, 30, up to 99 plans, and maybe you want to select which ones to run. So you can either check them one at a time or check all plans. That will check everything that you see in this list here. And then you can run all of the checked plans. Now, this leads me to another tip, which is when you have many, many plans, sometimes you want to run them in a particular order. If we could change that order, that would be really handy. So here's our moment of truth. When we hit run all checked plans, typically we'll get some sort of error. Let's see what happens here. If it runs smoothly, that's great. Yep, there is something that I've missed here. So let me see what popped up here. The internal dam breach inflow time series ends before the end of the simulation. Okay, luckily this is an easy one to fix. Again, I could go back and delete this out of the recording and have it just run smoothly, but this is what happens to hopefully all modelers. Maybe there are some people who do it perfectly the first time. I'm not one of those modelers, so I will hit close here and let's figure out where we've got a problem with internal dam breach inflow. So that's this flow file right here. So when I open this up, let's see, internal dam breach inflow. We'll click on flow hydrograph, and sure enough, I wish I could say I just made this mistake deliberately to demonstrate what we need to do and to show you these mistakes, but this was an actual mistake that I made. I had this data time interval at 1 minute. It's supposed to be 1 hour. So this is why it's always worth plotting the data so you can actually see the data here, make sure it's realistic on the time scale here. If I was in minutes, this would have come and gone way too quickly. So I'm going to say okay, and I guess while we're at it, let me just check all of these to make sure I've got 1 hour interval there, 1 hour interval there, yep, and finally the 1 hour interval on the precip, even though we've got that zeroed out, just to make sure that we're all good. Okay, so let's try this again. Check all plans, run all checked plans. Do we want to save that? I probably should have done what I typically recommend doing, which is to save often with the flow file. Luckily, it prompts me to apply that. It's going to be the same flow file that gets applied to both of these geometries. And now let's see what happens here as we start our pre-processing. So I won't record this whole thing. I'll probably just pause it while it's going through. But just to mention what it's doing in the background, every one of these 500,000 computational cells is now getting its properties saved. So no flow yet. What it's doing now is going through and saying at a particular elevation, if the water was in this, hypothetically, at a number of different elevations, at any given elevation that you pick, what is the corresponding wetted perimeter around the external cells where it's cutting cross sections from the LiDAR? What is the stage volume relationship? You know, at a given level, think about a reservoir or a dam where you've done a stage volume relationship. It is doing 500,000 stage volume calculations so that when there is a given flow elevation coming into a cell, it knows that corresponds to a particular volume. It's compiling the roughness coefficients and a whole bunch of other things. So again, we're just going to let it run here. I'll pause the recording while we wait for the pre-processing to finish, and then we'll talk about what's happening during the simulation. Now, one other tip that I forgot to mention when we pulled up this run multiple plans command would be to allow a date here. You could sort it by date, and then you could see which ones you wanted to run based on when you saved that particular plan. Okay, so this has now finished the pre-processing. So now we're going to move into the actual unsteady flow simulation part of this, which could take a while. So you'll see this tracking now are water surface errors. There's some pretty large errors in the very beginning of this one. And so one of the things that I'll do here is to pause this briefly so that I can scroll up here, and let's have a look at what we've got already before this runs all the way through. And I do recommend doing this. If you have a model run that's going to go for a long time, pause it in the very beginning and have a look and make sure it's doing what you wanted it to do. So if I scroll down here, I'll see which version of the software I'm using. It tells me here now which equation set that I've run, how many cores it's accessing, and now you'll see here my water surface error. Another tip, it would be great if we could see what these units are. So this is a water surface elevation in meters in our case. This is the error that's happening at this particular cell. And again, that error is vertical, I believe, in meters. And after this many iterations, you can change the number of iterations from the default. But after this number of iterations, it kicked this back and said, here are my residual errors. Now, a 4-meter error, that is pretty big. You may want to go back and start readjusting this, or if this is going to start running really slowly, you may want to go back and look at the overall number of grid cells that you've got in your model, or the grid size to try and speed this up a little bit. Okay, so I'm going to let this resume again, and we will talk about a couple of other things while this is running in the background. Now, another thing that I'm not going to do quite yet, but that you can do just to make sure you're on track, is to make a snapshot of the results, go into RAS Mapper and have a look. Now, the way we're setting up these videos, I'm not going to look at the results until we're in that unit, in the final session number 6. But this is something that you may want to do yourself, just to have an initial preview and make sure that you're not wasting your time. Maybe you did something in the very beginning to the initial conditions, or something that doesn't look the way it should, and maybe you don't need to wait for all of this. You could go ahead and make a snapshot, have a look at it, and make sure you're on track before you spend all the computational time waiting for this to finish. So you can tell already we're getting some massive errors, but look at the cell where these errors are occurring. So it's all the same cell. Now, if I'm getting an error at every single time step, then I don't know how many errors I've got in my model. It might be hundreds and hundreds of errors, and this is just the worst case. If you see one pop up and it's not happening every single computational time step, then that's probably the only residual error that's of concern. So when I see here, though, 17 meters, that at an elevation of 200 meters above sea level, the computed water surface elevation as it moves from one cell to the next is off by 17 meters. Yeah, that's a problem. And so again, we're modeling a massive tsunami here, and we're doing it at a 30-second time step, which is probably enough in the area of interest that we're looking at, but probably not enough where these dynamic situations are occurring. Now, the speed that this will be moving at is going to depend on your own hardware. You may be running twice as fast as mine, or you may be running half as fast as mine. So that's something that I'll link to another document about the optimization of your hardware that can help you decide, how many cores to use, and other settings that can help improve the speed. So while this is running in the background, I thought I'd pull up a couple of images of some Corps of Engineers projects, just so we can talk a little bit about the default settings and why they are what they are. I would recommend, and I guess this is just as an end user, if we could set these values as the default that corresponds to some of the more typical model scales that people use, I think that would be ideal. But we've also got to understand why these defaults are what they are. So my projects, and a lot of the ones that people send to me to review, are smaller than a typical Corps of Engineers project. But I'm not the one paying the bills. So even if it's frustrating to see diffusion wave come up as the default, for example, maybe there are some good reasons for doing that from the Corps of Engineers perspective. Say you were working on a massive river system like the Mississippi River, and you're setting up a model that's eventually going to take days to run. Maybe you want to get the right amounts of water moving around in the model before you're ever worried about detailed hydraulics. So in that case, maybe it makes sense to start with diffusion wave, and then you get more detailed after that. But for a lot of people who are new to HEC RAS, it might not be apparent that you'd need to have a look at the equation set at all. So some people may be working on a model scale where the computational time differences between different equation sets are not a huge concern, but you may as well get more accurate from the get-go, in my perspective. So at this point, it might be worth mentioning some of the types of projects that HEC RAS is built around, which are usually big river systems like the Mississippi, maybe the Missouri, or the Columbia. Technically, the Corps of Engineers only has jurisdiction over navigable waterways, whatever that means. Some people wonder why it's a military department at all. From what I understand, the Corps of Engineers is actually older than the US itself. It started as, I think, 3 engineers who helped out on Bunker Hill, and then it expanded with more capabilities back when you needed to dredge out the Mississippi River to get battleships up to what used to be the western border of the US at the time. I'll link to some history of that below if you want to read up on where this all came from. But again, where navigable comes in, if you want to hear a pretty wild story about that mandate, read about the people who challenged that definition along the LA River by kayaking it. Technically, they navigated it a while back. I'll also include a fun article about that below. So, but wrapping up the typical scale of HEC projects, and something that pulls us into current relevance, the recent addition of pipe networks might be a good example. As I understand, the Chicago district of the Corps of Engineers funded this part of the model. But if you look at some of the pipes, like this one that the Chicago district has to deal with, this is not your typical curb and gutter design, which is what we're all going to be using it for, centimeters at a time for a curb here or a graded inlet. When you're looking at that scale of things, you're debating the directions on the little slots in your graded inlet. These things are like 12 meters in diameter that the Chicago district has. So while this is running in the background, I thought we'd go back to the schematic and talk a little bit about how to set up some sensitivity runs. Now, HEC RAS can show you these relationships that we've got here with a basic summary. So again, this is a schematic description of what we've got right now. So we've got an existing condition geometry. We've got a project condition geometry. They're both linking to this tsunami at Disneyland, this Disnami. So I've got these 2 plans here. Now this linkage is helpful to visualize, and you can actually get HEC RAS to show you this linkage as well. So if we go back to our model files, while this is running, we can check all this. If I go under File, you can actually see a project summary. Now this project summary is essentially what I was just showing you, but it just tabulates it in written form here as a text file. So we can see we have G01 and U01 linked together there under Plan 1, G02 and U01 linked under Plan 2. So again, always worth comparing this and showing what you've got here just to make sure that we don't have any mistakes. Now there's another cool thing called compare model data. Now we're not going to use this at the moment to actually run a comparison, but when you pull this up, you can actually see graphically how this all works out. So I can see all of my other terrain files and see that they're not linked. And again, it's worth just pulling this up. If you're running something and batching up a whole bunch of things, have a look at this and see what you've got. When you get 30 geometries and 20 flow files and tons of terrains and plans, those lines are just really, really hard to see. So I'm not sure I really have any good suggestions on how to improve that visual, but I know it's really hard to follow at the moment, the way the lines all converge into one point. Hopefully somebody with better skills than me could make the connections simpler to trace. Like you see those airport connection charts in the back of the magazine in the planes, where it comes around and then comes to the right place instead of going right through it. Might make it easier to see. So that is another tip here. Improve the schematic file structure with some unique lines that you can kind of trace around and see what they all point to. So we won't take the time in this demo to set up sensitivity runs, but I thought we'd show the same schematic for some of the other runs that you might want to have a look at. So here are 5 typical things that you might consider changing. So let's call one of the runs that we've set up the baseline. How would the results change if you adjusted the grid size? What about the roughness coefficient, the boundary condition, the time step, or the equation set? So these are just 5 out of hundreds of things that you could check. But looking at these 5 things, let's talk about where these changes would get made, and hopefully that will help with any of the others that you might want to tackle. So grid size and roughness, those will both be in the geometry. Energy gradients would be in the flow file. And then time step and equation set would be in the plan file. So let's talk about how we would set these up. Maybe start with the grid size. So this will be the same for any parameters that are changed in the geometry. You would take your baseline, like we did with our existing condition where we first saved it as our project condition, and you might save one and then go finer, and you might save another and go coarser. So then you'd save the plan file twice more as well and link them all up. So the same would hold for roughness. Except there's two ways to do roughness. Sometimes you'll want to do it as a combination of both. You can either change the uniform roughness in the geometry itself, or you could do it in the map layers by just changing the land classification data. So you could have the same geometry linked up to different land classification files. So keep in mind, you can only have one land classification associated with a single geometry. So it might just be a duplicate of the same file for the geometry, but you'd still need to save that twice more and then link the geometries to the different layers. And similarly, you could change the geometry itself, but it might just be a change that's only reflected in the terrain. So you might have the same terrain copied twice, clone it, make some changes to it. The geometry file is exactly the same, but it's just linked to different terrain files. Now keep in mind, sometimes we want to compare the impacts of individual project elements, and we wouldn't necessarily call that a sensitivity. You'd just have different design cases. So if you're modeling the designs with no need to compare to existing conditions, you could have that design geometry and subject it to as many different flows as you want. If we wanted to do difference mapping or afflux mapping, those design features could either be reflected in the geometry, the terrain, or both, and you'd subject both of them to the same flow for comparison. So it might look like this. And you could treat infiltration the same way. Even though we technically think of that as flow, you would change this in the geometry associations. You could save a copy of identical geometries and just link them to different land classification layers that have higher losses, lower losses, or anything else that you'd want to change. So moving to the boundary condition values, you could save the flow file as two different names and then save two different additional plans to link to them, as long as we're only talking about the values changing and not the location or the name, which would mean also changing the geometry file to match. So in that case, you may need to save both the geometry and the flow file separately, and there would be no more linkages between them like you see in this case here. They're all independent. Now, for the plan file settings, like the computational settings, these are the easiest ones because you keep all of your other linkages between geometries and flows exactly the same. So you just save a new plan file, and that will hold for the time step, the equation set, or any other of the parameters that we just looked at in this session. No matter what you do, though, any comparison of results is going to require separate plans. So here's the setup for some of the other variables that you might want to test. Now, a lot of these things have default values, but you don't actually know what they are without some sort of calibration, like the weir coefficient for something that's not perfectly in the shape of a standard weir design. So you might want to check how your results are impacted within a reasonable range. That one's covered in the geometry. You might want to try different bridge modeling approaches, also covered in the geometry. Expansion and contraction coefficients are in the geometry, but maybe you also want to check the filter tolerance if you're running rain on grid. You may want to check for artificial depression storage in your terrain by pre-filling it with some artificial inflow or some precip, or starting ponds or reservoirs with different initial water levels. So that information would be stored in the flow file. The rest of these are in the plan, nice and easy, but dam breach parameters are interesting. Even though you'd typically access them through the geometry, they're saved in the plan. There's the max Courant number, which you could test with your variable time steps, also in the plan. And even though the filter tolerances are in the geometry, the calculation tolerances are in the plan, and you might want to try some adjustments to those. So these are just a few other things that I've broken down. And again, these are just a couple of ideas out of hundreds of things that you could potentially test and tweak in your model. So even if we just go back to our 5 basic sensitivities, we would start with baseline plan settings, geometries, and flow files. So that's the ones you see in red here. So this would be one plan. Now we were taking 2 different variations of the geometry for 2 different settings, so that would be 4 more. And then we take 2 different flow file settings for the boundary condition, and then 2 sets of 2 different values for the plan settings. So in the end, with these 5 sensitivities, as long as we're only changing one thing to compare against the baseline, that would leave us with 11 runs. So you look at the setup here, and how would they be linked together? Again, this looks very complicated in the beginning, but when you look at how these are linked, this is actually as simple as it gets compared to what you could have if you were running Monte Carlo analyses. Now, in that case, if we had 3 different grid sizes, 3 different roughness coefficients. Again, keep going with that. 3 times 3 times 3 times 3 times 3. We have 3 to the 5th. That is 243 potential model runs that we could have by linking all of these together. Now, I will include some links below for some Monte Carlo webinars where you can look at how to do that within HEC RAS and how to get into the settings and have it run all of these. But for a 2D flood model, honestly, your run times are probably going to be way too long to be able to do full Monte Carlos on a big flood model like the one we've got. If that's running for a couple of hours, think about how many hundreds of hours you'd have to run this model for. So if I have a look at our progress, I'm still getting this one cell with really bad errors. So I'll be interested to have a look at those. You can always zoom in on this particular cell in RAS Mapper once we get into looking at the results and find out what was going on right there. So I'm going to take a bit of a break while this is running. I'll pause the recording and we'll come back when the time bar has progressed a little further. So if you're following along, you may want to take a little bit of a break here as well. So now it's just finished up the first run, and you can tell it has unchecked the second box. We've moved into the second run, plan number 2, and it has to process this thing all over again because we've got some changes in our geometry. Now, once you've done this once, it won't have to do it again unless you make additional changes to the geometry, for the next model runs. So here's the pre-processing going on again. So this step wouldn't take quite as long if we only made changes to the flow file or to any other plan settings. So again, even if most of this is identical, out of these 500,000 cells, very few of them actually have a change. It's got to recompute every one of those stage volume curves for every one of the 500,000 cells in the model. So you can see here, it gives you this warning that the property tables do not yet exist. Once they exist, after it checks that, then it doesn't have to recompute that. So it told us how long that pre-processing took. While it moves into the actual simulation, we can already go back here now and have a look at a couple of things from the first simulation that finished. So I'll go ahead and open this one up. I'm going to go back in now that it has batched into this second one. That's now my active plan. Now, I definitely recommend do not be messing around with opening a plan or doing anything with a plan file while it is switching here. You can totally mess things up if you start opening up the wrong thing and then HEC RAS on its own tries to open up the next thing in the batch while you're messing around with saving or doing something like that. I would always wait until it is in the middle of its simulation before you start messing around. So don't do that while you're getting toward the end of your blue bar there. That can be a bit problematic. So now we're kicking off the second run here. Let's go in and have a look under the options at the previous file that it has already computed. So if you look under options, you'll see there's no runtime messages yet. They're being tracked here, but they're not saved yet for this next run. But let's go back to the existing condition, the existing flood here, P01. Now under this plan, you can now go under the options and these should be black where you can look at the computational log file and the runtime messages. Always look at these before you trust any of the results. So if I go to the computational log file, this is a text file that you can now see. It has written a BC001 file for us, which includes some more detail on the volume accounting. So the mass balance errors, which looks very small, which is a little concerning because we saw how bad some of these errors were, 20, 30, 40 meters of residual error. But at the same time, the mass balance error at the end, it seems like it could keep track of where all the water was. So in minus out equals storage. That was the case at the end of the model. So let's have a look at these actual messages. Let's have a look at the worst water surface error as we scroll down here and see certain cells tend to be the worst culprits throughout the entire simulation. So even though we had pretty big overall error here on the maximum water surface, I mean, very big, 30 meters of error, look at the volume accounting error. So this doesn't always tell you you've got a great model, but it does tell you that you've got some problems if you've got high values either here or here. So this model on my computer took about an hour and 38 to run. So I'm curious on your hardware benchmarking, how long other people take if you're running the same thing. Do let us know. We'll dive into more of the troubleshooting steps once we're looking at the results, but those are some things that we can take a look at in the meantime while the next plan is running. So my second plan has now finished running, so we can do the same thing and have a look at the log file and the tabulated errors. Looks like it took just about the same amount of time to run as the previous one. So if I go here under the options, check my log file, I can see my mass balance error in this case is very small. And if I go back here to the runtime messages, I can scroll down to the bottom of that, which we were just looking at, and see that I've still got a very bad maximum water surface elevation error here. So I've got to be very careful not to let this very low mass balance error be deceiving and make me think that I've got a great model, because I don't. So relative to this whole volume of water that came in and out of the model throughout the entire simulation window, these errors are not necessarily all that big. If you did start to see some errors in the 1% to 2% range, that might seem very low, but those are actually pretty bad models once it starts getting into 1% or 2%, because that's just water that it couldn't keep track of, and it shows that there are some bigger problems with the rest of the model. Now, one final tip that I'm not sure if I mentioned before is with these plan files. When I'm trying to open them up, in this case, I've only got two, so it's very easy. But I think I've mentioned that I've got a lot of models where I've maxed them out with 99 plans. And so if I want to add something new, I have to take something out. And my new ones then get stuck somewhere mixed in with the old ones. They get renumbered. And it can be a real pain to find the latest ones. So being able to move these around somehow, or to renumber them, or group them to get the active runs together, or maybe even just being able to sort these by the save date would be very handy here. So thanks for joining us for part 5. Hope you've seen with this discussion about plan files why some of these settings matter so much. We'll follow up with part 6, our final part, where we look at some of the results in RAS Mapper and try to determine, are these results any good? So hopefully this has been helpful. Maybe you feel like you've run a race with these videos, or maybe you feel like we've gone into overtime with a soccer match. I know we're packing a lot of material into these, but hopefully you're able to adjust the playback speed as needed to suit your own preferences. Sometimes you'll see people model something in software that they know really well. It'll be calibrated to an event that they've observed, and then they try running the same thing in HEC RAS, and it'll look like it's way off, and it might look like it's giving bogus answers. And if you don't know which settings ought to be tweaked for a given situation, you might think that these answers are no good. But hopefully with this video, you've been able to see a couple of things in the plan that we need to be aware of, because if you do just run it out of the box, there are quite a few things, as you've seen, that we may need to keep in mind about the limitations. So with that, we look forward to seeing you in part 6, where we'll go through all of the results in RAS Mapper and see how we do with that.